Today we're going to be talking briefly about U-substitution for our anti-differentiation process. U-substitution is mainly used when you had a chain rule that you need to undo. So in order to undo a chain rule, so generally you're going to be having larger exponents, with, some sort of function within another function that we need to take the antiderivative of. So let's just kind of get right into an example. If I have the antiderivative of x squared minus 1 to the 5th dx. Now, we talked in our first antidifferentiation lesson about how, let's say we had just x plus 1 squared dx that we were taking the antiderivative of. Well, if I have something to the second power, okay, that's something that I can very easily expand out. So I can have x plus 1 times x plus 1 and FOIL that. So I have x squared plus 2x plus 1 dx. And then I can take the antiderivative of each piece. Okay? However, so if I have something like with a square, I can very easily FOIL that. But in this case, I have an x to the 5th power. That scares me a little bit because I do not want to have to spend the time to multiply this binomial out 5 times. So therefore, that's why we need this rule for our antiderivative of a chain rule. So we use U-substitution. So what I'm going to do is I'm going to let U be some sort of function, and generally it's the function that is the most complicated and the one that's kind of your almost g of x function. So it's your inside function most of the time. There are some circumstances where it's not, but most of the time it's your more complicated function. In this case, I have an x squared minus 1 and I have an x. Well, my more complicated function is that x squared minus 1. So I'm going to make u equal to x squared minus 1. Now what I'm going to do is I'm going to take the derivative of that u. So the derivative of x squared minus 1 is 2x dx. So after I have that term, I want to make what is over here identical to what I have left in my equation. Okay, so let's talk about this again. Right now, if I was to replace, let's backtrack for a second. If I was to replace x squared minus 1 with u, right now I have u to the 5th. That leaves me with this x and this dx. Well, I have x and dx right here. So in order to get x dx by itself, I need to divide both sides of this statement by 2. So that means that my x dx from the original statement is equivalent to, I could replace with 1/2 du. Now we've talked about before how these coefficients, these numerical coefficients, can actually come out in front of my integral symbol. So really, I'm going to be taking the antiderivative of u to the 5th, and I have my du statement because I have a u variable, so I need a du to represent the derivative of my u variable. So once I have that done, I can now take the antiderivative of u to the 5th. Well, the antiderivative of u to the 5th would be u to the 6th over 6. Whoops. My mistake. I did not mean to put that integral symbol in there. We should not have that integral symbol there once I have taken the antiderivative. So we become u to the 6 over 6 plus c, but I also have that 1/2 that was my coefficient from before. So right at this point I have u to the 6th over 12 plus c. Now, that's not my final answer though, because my original problem was given to me in terms of x. Now, I need my final answer then to be in terms of x. So what am I going to do? I'm going to replace u with what I had u equal to over here, which was x squared minus 1. So I'm going to go back over, and instead of u, I'm replacing u with x squared minus 1, what that u is equivalent to. Divide it by 12 and plus c. And that is my antiderivative statement. That's my answer. Now you have to kind of think ahead when you're doing these U-substitution problems. Here's my answer, but let's go back for a second just to the original problem. So my original problem stated x squared minus 1 to the 5th power dx. Okay. Let's for a second say that this x was not there. So then the question becomes, can I still do the u substitution? Well, let's think about this again. My u would still be x squared minus 1, okay? But my du is now still again 2x dx. Here is the issue. When I solve for what's left in the equation, meaning, let's start replacing. I have u to the 5th. What's left is my dx. So I have dx over here. And if I divide it over, I'd get 1 over 2x du. Here is my issue. When I go to replace this dx with its du equivalent, I cannot have an x variable still in my equation. Because right now, what I'd be replacing dx with would be 1 over 2x du. This does not work because of that x variable. That means that in this case, u substitution would not work. So then the question becomes, how would it be done? Well, hopefully you don't get a question like this, but the only other way to then go about solving this problem would be to FOIL this whole thing out, which would be unfortunate, which is why you don't often see questions like that. So just make sure you're keeping an eye out for that. In order to do u substitution, I need my original u statement, but then I need to look ahead to make sure that if my du has another x variable in it, I need that x variable somewhere in that original problem. So let's try out another example. I have got the antiderivative of 3x minus 2 to the 4th dx. Okay, well, this looks like I could possibly have the same issue that we just talked about, but let's double check. So my u value, what is inside the parentheses, is 3x minus 4, not 4, 3x minus 2. So the du of this would be equivalent to 3 dx. So let's start replacing what I have. So 3x minus 2 gets replaced with u. And I only have dx left over. Okay, well, to get dx by itself, I'd have to divide both sides by 3. So does this work? Well, now that I have dx, I replace dx with 1/3 du. So the question becomes, are there any x values left in the statement? The answer is thankfully no, therefore the u substitution did work. So I'm going to bring that 1/3 out in front, as we did before, because I'm not actually taking the antiderivative of the 1/3. That is a coefficient that is just going to follow us down. The antiderivative of u to the 4th, well, again, we add 1 to the exponent, divide that term by the new exponent, and add our plus c. So I have u to the 5th over 15 plus c, but please don't forget we need to substitute back in what our u value actually represents in terms of x. So 3x minus 2 to the 5th power over 15 plus our lovely c is going to be my final answer. Let's jump now to another one. So I have the antiderivative of x squared times the square root of 1 minus 4x cubed. So this one looks a little bit more complicated. So let's think of this in terms of different aspects. Well, I never like taking the derivative or antiderivative of a square root. So I'm going to rewrite this instead of a square root. I'm going to rewrite it in terms of a rational exponent. So this is going to be 1 minus 4x cubed to the 1/2 power. Now again, my more complicated term out of x squared and 1 minus 4x cubed. Generally, the one with the higher exponent is my u value, which is 4 minus x cubed. The derivative of that would be negative 12x squared dx. So let's start replacing what we can. So 1 minus 4x cubed to the 1/2 is going to be u to the 1/2. That leaves me with x squared and dx. So that's what I need, this du statement. That's what I need on the right-hand side. X squared dx, which I do have. I have x squared dx. So in order to get that x squared dx, I have to divide both sides by negative 1/12. So now I can replace my x squared dx in my original antiderivative statement with 1 over negative 12 du. Question, do I have any x values left in my new integral statement here? Nope, none. Great, so now we proceed on. Bring my coefficient out in front. And now let's do our antiderivative. As always, my coefficient is going to follow us down. U to the 1/2. Well, again, we're going to be adding the equivalent of 1, which in this case would be 2/2. So that's going to become u to the 3/2 power divided by 3/2. But instead of dividing by 3/2, I would much rather skip a step for myself and instead multiply that by the reciprocal of 3/2, which would be 2/3. So I'm just skipping a step for myself. So instead of dividing by 3/2, we multiply by its reciprocal. So now I'm going to simplify this a little bit. I can simplify the 2 and the 12. So I end up with negative 1 over 18 u to the 3/2 power plus c. But again, as always, we need to go back to in terms of x. So negative 1 over 18, u is equivalent to 1 minus 4x cubed plus c. And that would be our final answer. Let's just do one more before we end our video. Okay, so let's go to, I'm taking the antiderivative of x to the 1/2 power, x to the 3/2 plus 2 to the 9th dx. Okay, so as always, start out with between x to the 1/2 and x to the 3/2 plus 2, the higher exponent, the more complicated expression is x to the 3/2 plus 2. The derivative of that would become 3 over 2 x to the 1/2 dx. So when I'm replacing, my original u term is going to be u to the 9th. I am left with x to the 1/2 dx, which is right here. How am I going to get that? Well, instead of dividing by 3/2, let's multiply both sides by the reciprocal so that those fractions will cancel out. And so I'm left with 2/3 du equal to that x to the 1/2 dx I have to replace. So x to the 1/2 and dx is going to be replaced with 2/3 du. And as always, the 2/3 comes out in front. I have u to the 9th du, and that's going to become u to the 10th over 10 plus c. So before we combine, I'm just going to simplify, factor out a 2 here, and I end up with u to the 10th. U to the 10th over 15 plus c. And for one last time, we are going to be substituting back in for u what u is equivalent to, which is x to the 3/2 plus 2 to the 10th power over 15 plus c. And there's my final answer. Okay? I hope this has been helpful for you. We will continue on with more practice in class.